Stand at Ground Zero, New York City. One World Trade Center rises 1,776 feet. Deliberate height honoring Independence Year. This building contains promise. It will never fall again. That promise lives in 45,000 tons of structural steel and 200,000 cubic yards of concrete. But concrete alone crumbles under stress. What gives it strength are 300 million pounds of steel rebar, ribbed bars running through every column, every beam, every floor. Each bar began as scrap metal melted at 3,000 degrees, rolled into ribbed shape, cut to exact length, trucked from South Carolina mill to Manhattan, and positioned with surgical precision. How does junked car become foundation of America's safest building? Why does rebar require ribs instead of staying smooth? Stay with us. You'll witness electric arc furnace creating artificial lightning and discover rebar's critical secret. Those ribs aren't decoration, they're mechanical bond preventing concrete from tearing itself apart. Nucor Steel Berkeley in South Carolina produced most rebar for One World Trade Center. This facility processes 2 million tons of scrap steel annually, and enough to build 12 Empire State Buildings yearly. The scrapyard stretches quarter-mile. Mountains of crushed cars, demolished buildings, retired appliances, old rebar from previous demolitions. Giant electromagnets lift entire automobiles, dropping them into sorting lines separating steel grades. Every day, 600 trucks deliver scrap. Every day, 400 trucks leave carrying finished rebar. Walk the scrap processing area. Shredders pulverize cars in 8 seconds. Same time it takes to read this sentence. Hydraulic shears cut structural beams like scissors through paper. The noise is relentless. Metal tearing metal, magnets clanging, conveyor belts grinding. One supervisor explains, "We see America's past arriving daily. Cars people drove to work, buildings where they lived, bridges they crossed. We melt history and rebuild tomorrow." For World Trade Center project, this facility operated 24/7 for 3 years straight, producing 3,000 tons monthly, enough rebar to circle Manhattan Island 40 times. The electric arc furnace transforms scrap into liquid steel through controlled lightning. This vessel, 40 feet diameter and 30 feet deep, contains 3 graphite electrodes 2 feet thick descending from roof. When 90 megawatts flow power for 70,000 homes, arcs jump between electrodes and scrap, generating 5,800 degrees. The scrap melts in minutes. Watch through protective glass as metal liquefies, glowing white hot then orange as temperature stabilizes. 200 tons of scrap loads per batch. The electrodes pierce the pile, current flows and artificial lightning strikes continuously. The sound resembles continuous thunder. The heat radiates through observation room despite water-cooled walls. Oxygen lances inject pure oxygen at supersonic speeds, burning impurities. Carbon oxidizes to gas, sulfur evaporates. Phosphorus combines with lime-forming slag that floats atop molten steel. Temperature control is absolute. Too hot wastes energy, too cool leaves impurities. Computer systems adjust power and oxygen flow thousands of times per melt, maintaining exact chemistry required for construction-grade rebar. Tapping releases 200 tons of liquid steel into ladle, refractory-lined bucket mounted on railcar. The pour takes 8 minutes, continuous stream of glowing metal creating updrafts lifting dust into air. Workers monitor from shielded stations, faces illuminated by orange glow. The steel, now 3,050 degrees, travels to continuous caster where transformation into solid bar begins. The caster pours molten steel into water-cooled copper mold, oscillating rapidly. As steel contacts mold, outer shell solidifies while interior remains liquid. The strand, continuous ribbon of solid steel, emerges from bottom, bent gradually from vertical to horizontal through roller system. Torches cut the continuous strand into billets 20 feet long, each weighing 4 tons. These billets, still glowing red at 1,800 degrees, feed directly into rolling mill. The entire process from scrap to billet takes 90 minutes. For WTC project, Berkeley ran 3 melts daily, producing 18,000 tons monthly during peak construction. The rolling mill transforms square billets into ribbed rebar through precision violence. The billet enters roughing stand where rollers squeeze and elongate it, reducing thickness while increasing length. Each pass through successive roller stands further reduces diameter. The steel, maintained at 1,600 degrees, glows orange-red, extending like taffy under roller pressure. 22 passes transform 4-ton billet into 500 feet of rebar. But here's where rebar gets its identity: the ribs. Special roller dies emboss transverse ribs and longitudinal ridges onto surface. These aren't decorative. The ribs increase surface area by 40%, creating mechanical bond with concrete. Smooth bar would slip under stress. Concrete would crack and fail. Ribbed bar locks into concrete through friction and mechanical interlock. The rib pattern follows precise standards: height, spacing, angle, all controlled to thousandths of inch. For WTC, specifications demanded grade 75 steel, yielding at 75,000 psi, 3 times stronger than standard residential rebar. After rolling, the rebar, still 800 degrees, enters cooling bed where water jets control cooling rate. Fast cooling creates hard but brittle steel. Slow cooling produces soft but weak steel. Controlled cooling achieves optimal balance. Computer systems adjust water flow based on bar diameter, steel grade, ambient temperature. The bars cool from orange to black in minutes, steam rising in clouds. Then comes straightening. The hot rolling process introduces slight curves. Straightening machines grab bars between sets of rollers positioned at angles, pulling and pushing until perfectly straight. Deviation under 0.01 inches per 40 feet. Next, shearing machines cut bars to exact lengths. For WTC, typical lengths were 40 and 60 feet, sized to fit concrete forms with minimal waste. Flying shears cut moving rebar at speeds exceeding 20 feet per second. The cut must be square, clean, burr-free. Each bar gets stamped with grade marking and mill identification. Quality control happens continuously. Samples from every heat, every batch of melted steel, undergo testing. Tensile machines pull specimens until they break, measuring yield strength, ultimate strength, elongation. Chemical analysis verifies carbon, manganese, silicon content. Dimensional inspection confirms rib height, spacing, and bar diameter. Every bar carries traceability, heat number linking it to specific melt, specific chemistry, specific mechanical properties. For One World Trade Center project, quality standards exceeded normal construction. The Port Authority required additional certifications, independent testing, complete documentation. Rejected bars got remelted. No shortcuts existed. One quality inspector recalls, "Every bar we shipped could end up in critical structural element. We tested knowing thousands of lives would depend on our work being perfect." The facility maintained 99.8% acceptance rate, meaning just 2 bars per thousand required remelting. Rebar's invention dates to 1850s France, when Joseph Monnier, a gardener, reinforced concrete flower pots with iron mesh. He discovered concrete's compression strength, combined with iron's tensile strength, created superior material. By 1900s, rebar became standard in construction. The ribbed surface pattern emerged in 1930s after engineers realized smooth bars failed under dynamic loading. Earthquakes, wind, vibration caused concrete to slip along smooth bars. One World Trade Center's foundation began in 2006, final steel placed in 2012. During construction, 600 trucks daily delivered materials to Manhattan site. Rebar arrived on flatbed trucks, each carrying 25 tons, 40 to 50 bars per load. Cranes lifted bundles to specific floors where iron workers tied bars into 3-dimensional cages matching structural drawings. For the concrete core, building's spine, rebar spacing was 4 inches on center in both directions, creating steel mesh so dense you could barely see through it. Environmental impact shows interesting paradox. Producing rebar from recycled scrap uses 60% less energy than making steel from iron ore. Berkeley facility prevented mining 200,000 tons of iron ore annually. Yet steelmaking remains carbon intensive. Melting metal requires massive electricity. Each ton of rebar generates 1.8 tons CO2 emissions. For WTC's 300 million pounds, that meant 270,000 tons CO2, equivalent to annual emissions from 30,000 cars. Here's the secret we promised. Rebar ribs create mechanical bond, but their real genius is crack control. Concrete always cracks. Thermal expansion, settling, loading all cause microscopic fractures. Smooth rebar allows cracks to propagate, widening until failure. Ribbed rebar intercepts cracks, distributing stress across multiple ribs, preventing single crack from becoming catastrophic failure. Those ribs transform concrete from brittle material into ductile system that bends before breaking. At WTC, this matters profoundly. The building must survive impacts, explosions, earthquakes that would destroy conventional structures. From South Carolina scrapyard to Freedom Tower rising above Manhattan, the transformation completes. Nucor Berkeley melted America's discarded metal and reformed it into symbol of resilience. That rebar, 300 million pounds of it, creates skeletons stronger than original towers. Every bar positioned perfectly, every connection inspected, every pore documented. The building stands because thousands of workers understood. This isn't just construction, it's promise. Promise that engineering will triumph over terror, that steel and concrete and human determination can create something genuinely unbreakable. Those ribs running through every column aren't just preventing concrete failure, they're preventing failure of a different kind. The failure to rebuild, to remember, to rise again. Every year, billions of people around the world press the same pedal, and they don't even realize it was slowly killing them for decades. What was supposed to save lives quietly filled the air with poison. Why did a material once considered perfect vanish almost overnight? And what replaced it? There's one detail brake pad ads never mention, but it's what determines whether your car stops in that critical split second. Today, these pads withstand hell itself, don't smoke, and leave barely a trace. But the road here was deadly dangerous. Stick around till the end, and you'll discover which hidden component once cost millions of lives and why modern factories guard their formulas like state secrets. In the 1920s, every brake pad contained asbestos, fibers that could handle 1500 degrees Fahrenheit and wouldn't wear out. But every tap of the pedal released microns of poison into the air, settling in the lungs of drivers and pedestrians. By the 1990s, asbestos had killed millions. Lung cancer, mesothelioma. Europe banned it first in 1998. Manufacturers scrambled to find a replacement. Organic compounds made from rubber, glass, and metal fibers. The first non-asbestos pads braked worse, overheated at 750 degrees, and released the rotor. But it was a start. Today, the top choice is ceramic composites. The base is ceramic made from silicon nitride and silicon carbide, mixed with copper fibers for heat dissipation. The material withstands 650 degrees without deforming, doesn't squeal, and doesn't dust. Ceramic makes up 40 or 50% of the mass, reinforced with steel fibers for strength. At 500 degrees, regular pads smoke. Ceramic ones stay cool as ice. In this massive plant, something is born that'll save your life on the road. Manufacturing ceramic brake pads isn't just mixing powder with binder. It's precise science involving pressure, fire, and high-precision machinery. Each pad weighing 7 ounces has to survive 600 degrees of hell, not crumble, and not let go of the rotor. Let's break down the process step by step, from raw materials to finished kit. Everything starts with hoppers full of powders. The main ingredient, ceramic, meaning silicon nitride silicon carbide, a white powder hard as diamond. They add copper fiber for heat dissipation, thin threads the width of a hair, graphite for smooth grip, reinforced glass for strength, barium sulfate for stability at high temperatures. Each recipe is a factory secret, like the Coca-Cola formula. In giant mixers with a 500-gallon capacity, powders are combined in precise proportions. They add liquid wax-based lubricant, 5 or 7% by weight. The mixer spins for 30 minutes at 50 revolutions per minute, transforming dry powder into a uniform wet mass, like bread dough. Temperature is held at 100 degrees so the lubricant doesn't freeze. The result is raw dough weighing 1,100 pounds, ready for forming. The mass goes into a rotary press, a machine with 20 tons of force. They pour 550 grains of the mixture into a metal mold measuring 6 by 2.5 by half an inch. The top plate descends with 285,000 pounds per square foot of pressure, like parking a tank on your palm. In 10 seconds, the dough compresses into a monolithic green blank, 3/4 of an inch thick. The pressure squeezes out all the air, creating a density of 175 pounds per cubic foot. The press runs in cycles, 60 blanks per hour. Each comes out perfectly smooth with a friction surface angled at 5 degrees for better disc contact. The blank's still brittle as cheese, but it already has the shape of the future pad. The most critical stage? Sintering. Green blanks go onto steel trays, 50 pieces each, then get pushed into a tunnel kiln 100 feet long. Temperature rises gradually. At peak heating, 4 hours in, the ceramic melts. Copper fibers fuse. Graphite crystallizes. Total sintering time, 12 hours. Finished pads, gray-silver monoliths. Go to inspection. A laser scanner checks dimensions accurate to 1/100th of a millimeter. Ultrasound checks density and cracks. 2% get rejected. Next, grinding. The machine removes 0.5 millimeter from the friction surface for perfect geometry. Edges get rounded to prevent squealing. They apply a protective coating, a thin layer of molybdenum disulfide for that first soft breaking. Laser marked, then assembled into kits, 4 pads plus springs plus backing plate. The final test, the simulation stand. The pad is pressed against a disc spinning 2,000 revolutions per minute for 200 cycles. Acceleration, then hard braking up to 6,000 degrees. They check wear, squealing, dust. Ceramic pads pass without smoke. Metal ones squeal. A finished pad wears out after 30,000 miles. That's normal wear. With aggressive driving, it wears out after 18,000 miles. The U.S. market operates with 131 facilities, which has decreased by 0.6% in recent years due to automation. Production is tied to the automotive industry. Rising car sales drive demand, especially for pad replacements in trucks and passenger vehicles. Key trends: shifting to eco-friendly materials without copper. California capped it at 0.5% starting in 2025, which cut pollution by 28% statewide. Imports matter, but tariffs affect local production. The leaders are the southern U.S., specifically Texas, Alabama, Tennessee, with Ford and GM plants. The European brake pad market shows steady growth at an average annual rate of 4.7% through 2028. In Germany, the market leader volume will hit nearly $320 million by 2028. France is growing at 5.5% annually, the UK at 3.8%. Metallic pads are still popular and hold 25% of the EU market because they're cheap for trucks and Porsches. But their dust is a problem. Steel and copper settle on roads, get into water and lungs. Ceramic cuts emissions by 80% compared to these semi-metallics. Now, besides asbestos and metallic pads, there was an attempt to make organic ones. These are pads from the 2000s, the first mass replacement for asbestos. The base is synthetic rubber, fiberglass for reinforcement, Kevlar or aramid fibers for strength, plus barium sulfate and graphite. The soft compound gave a quiet bite. Little dust, didn't scratch rotors. But at 550 degrees, they lose 30% of their stopping power, which works for daily driving but not for sport.
Every year, over 40 million new gadgets hit the market, but almost nobody knows about the metal that makes them actually work. Why can a tiny element buried deep underground literally launch an entire civilization, from the Bronze Age to modern electronics? And what do ancient swords, tin cans, and your smartphone have in common? In this video, we're uncovering the secret of tin, the metal that built the past, runs the present, and hides a fact you've definitely never heard before. Stick around until the end. That's where the real mystery reveals itself. Tin isn't just some new trend. This is a metal with a deep-rooted history spanning thousands of years. Its discovery sparked a genuine revolution that forever transformed the course of human civilization, launching what we call the Bronze Age. Picture this. Ancient craftsmen learned to extract copper and forge tools from it. But copper was soft. Then, whether by accident or experimentation, they discovered something remarkable. If you added a little bit of another then unknown metal to molten copper, tin, the alloy became incredibly strong, hard, easier to cast, and held a sharper edge. That metal was tin. The copper-tin alloy became known as bronze. Bronze swords, shields, tools, jewelry, all of this suddenly became accessible, giving ancient civilizations a massive advantage. It was a true technological leap that transformed warfare, agriculture, and art. Tin became so valuable that real battles were fought over its deposits, and trade routes to tin mines, like those in Cornwall, Britain, were incredibly important. Over the centuries, tin stayed valuable. It was used as a coating for other metals to protect them from corrosion. For example, tin plate, a thin sheet of steel coated with tin, which was used to make cans. It was also used to make soft solders that joined metals together, and in the production of mirrors, and even to create organ pipes and coins. But its true renaissance came in the 20th century with the rise of electronics. Over 50% of all global tin consumption goes to this industry. Solder. That's its main job. Your computer, smartphone, TV, inside them, thousands of electrical components are connected together. These connections are made using solder, which is usually an alloy of tin with other metals, like lead in the past, now mostly with copper, silver, or nickel. Tin is perfect for solder because it has a relatively low melting point, which makes it easy to melt and form connections without damaging sensitive electronic components. Tin also wets metals, meaning it easily flows across the surface, creating a strong electrical and mechanical bond. It's got great electrical conductivity too, and it's corrosion resistant.
Modern electronics use what's called lead-free solder, which is a huge step forward for the environment. Tin is the main component in these alloys. Without reliable soldered connections, the entire complex architecture of microchips would simply fall apart, and your gadget would turn into a pile of useless parts. Tin is used to coat other metals, especially copper, on printed circuit boards. This protects the copper traces from oxidation and makes the soldering process easier. It's also used to coat connectors, which improves their electrical conductivity and corrosion resistance. Tin isn't a super common element in the Earth's crust. Its primary mineral is cassiterite, basically tin oxide. It's a pretty dense mineral that's often found in placer deposits, meaning you can extract it from river sediments or ancient coastlines. Over 70% of the world's tin production is concentrated in 4 countries across Southeast Asia and South America: China, Indonesia, Myanmar, and Peru. This makes the tin market highly sensitive to political and economic events in these regions. Tin mining begins with the exploration phase. Geologists, armed with modern technology, conduct surveys, drilling, and analysis of soil and rock samples to find locations where cassiterite concentrations are high enough for economically viable extraction. Once a deposit is identified, development begins, which can follow 2 main paths depending on the type of deposit. The first and most common method of tin mining is from placer deposits. Picture this. Over millions of years, cassiterite washed from bedrock by water and erosion accumulated in riverbeds, at the bottom of lakes, or on ancient seashores.
It settled like sand in what's called placer deposits. Extracting from these deposits is often way simpler than digging underground mines. Here, they use massive dredges, floating factories that scoop up tons of soil and gravel from the bottom of waterways, or they deploy hydraulic monitors, powerful jets of water under high pressure that blast away soil from riverbanks or hillsides containing cassiterite. The blasted rock then flows to primary processing, where gravity methods, exploiting density differences, separate the cassiterite from lighter waste rock. Think industrial-scale gold panning, only gigantic. The second method? Extracting from primary deposits, where cassiterite sits directly in solid rock. That's where traditional underground mines come in, same as mining any other metal.
Miners drill tunnels and boreholes into the rock, use explosives to blast apart the ore vein, then loaders collect the ore and haul it to the surface. It's a more expensive and complex operation, requiring heavy-duty equipment and strict safety protocols. Once extracted, the ore, no matter where it came from, heads to a processing plant. First, it's crushed and ground into a very fine powder in mills to free the cassiterite crystals from the surrounding rock. Then various enrichment methods kick in. The first method, gravity separation. Since cassiterite is a pretty dense mineral, it gets separated from lighter minerals using water. This can happen in jigs, concentration tables, or spiral separators.
The second method is flotation. Sometimes, for further enrichment or to separate cassiterite from other minerals, flotation is used, where cassiterite selectively sticks to air bubbles and rises to the surface as foam. As a result of all these processes, a tin concentrate is obtained that already contains more than 50% cassiterite, or even more. This concentrate then goes to a metallurgical plant to produce pure metallic tin. Here, the concentrate, which is tin oxide, is mixed with coal, which acts as a reducing agent, and fluxes. Fluxes are substances that help separate impurities. This mixture is heated in special furnaces to high temperatures, typically around 2400 degrees Fahrenheit. At these temperatures, the carbon steals the oxygen from the tin oxide, releasing pure metallic tin, which melts and flows to the bottom of the furnace.
The molten crude tin still contains impurities from other metals, so it goes through another crucial stage, refining. This can be thermopurification, where the lead is heated to specific temperatures so other metals separate out or float to the surface. Or more often, electrolytic refining, which allows for extremely high tin purity. High purity means almost 100% in this case. Can you believe that? This is critically important, especially for the electronics industry, where even the tiniest impurities can affect conductivity and component reliability.
The metal that protects all other metals from rust. Picture this: 70% of the world's steel is covered with a thin layer of zinc. Bridges, skyscrapers, cars, ships, everywhere zinc stands guard, taking the hit from corrosion. Every second, the world produces 1.5 tons of zinc, 14 million tons per year. It's the fourth largest metal by production volume on the planet, after iron, aluminum, and copper. But they extract it unusually. Zinc is vaporized at 1,800 degrees Fahrenheit, and the vapor is collected. Yes, the metal turns into gas. How do they turn gray ore, mined a mile underground, into a bluish-silver metal that sacrifices itself for others? You'll learn why the ore burns in furnaces, how they collect metallic vapor, and why without zinc, the entire infrastructure of the planet would collapse. Watch till the end. The finale will show what's behind every galvanized beam. This is the story of the bodyguard metal that took on the corrosion of the entire world.
A mile underground, darkness, explosion, tons of rock crash down. This is a zinc mine, one of hundreds around the world where ore for the guardian metal is extracted every day. Underground dump trucks with 50-ton capacity haul ore to the mine shaft. An elevator the size of a house lifts the rock to the surface. The ore is dark, almost black. This is sphalerite, zinc sulfide. Crystals with diamond-like brilliance, but the metal content is only 10 to 15%. The rest is waste rock. Trucks carry the ore to the processing plant. The transformation from stone to metal begins. Massive cone crushers as tall as a 3-story building grind ore chunks the size of cars. The noise is deafening. The rock is crushed into gravel the size of fists. Then the gravel goes into ball mills, rotating steel drums 16 feet in diameter, filled with steel balls the size of watermelons. The drum rotates, balls fall, grinding the ore into fine powder. After 8 hours of grinding, you get gray dust, particles the size of sand grains. The ore powder is mixed with water, creating gray liquid slurry called pulp. It's pumped into huge flotation machines, tanks with volumes of 3,500 cubic feet. Chemical reagents are added, foaming agents and collectors. Mixers are turned on and air is fed from below. The magic of flotation begins. Millions of air bubbles rise through the pulp. Particles of sphalerite, zinc ore, stick to the bubbles and float up. A gray foam forms on the surface, 20 inches thick. This foam contains zinc. Waste rock settles to the bottom and is drained off. The foam is collected, filtered, dried. The result is concentrate, powder containing 50 to 60% zinc. From 100 tons of ore, you get 10 to 15 tons of concentrate. This concentrate is loaded into rail cars and shipped to the smelting plant. There begins the real alchemy, turning powder into molten metal. And this is a process where metal turns into vapor. At the plant, concentrate is loaded into fluid bed roasters, massive steel cylinders 66 feet tall. Hot air under pressure is blown in from below. The concentrate powder lifts up, floating in the air like dust. Gas burners are ignited. Temperature rises to 1,650 degrees Fahrenheit. The zinc sulfide ignites. Yes, the ore burns. Sulfur oxidizes, releasing enormous amounts of heat. Sulfur gas flies up the stacks. It will be captured and turned into sulfuric acid. And zinc sulfide transforms into zinc oxide, a gray-white powder. The temperature in the furnace is so high that the walls glow red. The roasted concentrate, zinc oxide, is cooled and mixed with coke, crushed coal. The proportion, 3 parts oxide to 1 part coke. This mixture is loaded into vertical retort furnaces, steel towers 50 feet tall, lined inside with refractory silicon carbide. Heating begins. Temperature starts climbing. 1,800 degrees, 2,000 degrees, 2,200 degrees. At 2,200 degrees Fahrenheit, carbon begins taking oxygen away from zinc oxide. A reduction reaction occurs. But something amazing happens. Zinc doesn't melt. Its boiling point is only 1,665 degrees, but the furnace is at 2,200. So zinc immediately turns into vapor, metallic vapor. Inside the furnace, atoms of gaseous zinc are flying around. The vapors rise up and exit the furnace through piping. They enter a condenser, a special cooled chamber. Temperature in the condenser is around 840 degrees, below boiling point but above melting point of zinc. The vapors condense. Drops of molten zinc settle on the condenser walls, glowing orange. Liquid metal flows down the walls and collects in a receiver. This is crude zinc, contains impurities of lead, cadmium, iron. Purity around 98%. Each furnace produces up to 100 tons of zinc per day. The metal is cast into molds. The result is ingold bars weighing 55 pounds each, silver gray with a bluish tint. For some applications, pure zinc is needed. Then it's refined, purified by distillation. Crude zinc is heated to boiling in a vacuum furnace. Under reduced pressure, boiling point drops to 1,300 degrees. Zinc vaporizes while impurities remain solid. Zinc vapors are condensed in a cooler. The result is refined zinc with 99.99% purity. This zinc is cast into ingots. On the ingot surfaces, a characteristic pattern forms, crystalline designs resembling frost flowers on glass. This is called zinc flowers. Ingots are stacked. Zinc is ready for use. But its main application awaits in hot-dip galvanizing baths. There, steel products will receive corrosion protection. The process looks impressive, like baptism of metal by fire. A steel beam 40 feet long is immersed in a bath of molten zinc. Temperature 840 degrees. The beam completely disappears in the silvery liquid. Chemical reaction begins instantly. Zinc reacts with iron on the steel surface, forming a layer of intermetallic compounds, a solid alloy of zinc and iron. This layer bonds permanently to the steel. On top, a layer of pure liquid zinc. The beam is held in the bath for 1 to 2 minutes. Then it's pulled out. Excess molten zinc drains back. In air, the coating quickly solidifies. The surface becomes silvery, matte, with the characteristic pattern of crystals, zinc flowers. Coating thickness from 2 to 8 thousandths of an inch. That's just fractions of an inch, but it's enough. The galvanized beam won't rust for 50 to 70 years. Even scratches aren't scary. Zinc continues protecting. It's about electrochemistry. Zinc is more active than iron. When corrosion begins, zinc oxidizes, not steel. Zinc sacrifices itself, protecting iron. This is called cathodic protection. World production of galvanized steel, 55 million tons annually. This uses 6 million tons of zinc. Without zinc, modern cities would be impossible. 70% of zinc goes to protecting steel. But there are other applications. Brass, an alloy of copper and zinc, has been known for thousands of years. Contains 15 to 45% zinc. Golden, strong, easily worked. Brass is used for plumbing fixtures, musical instruments, cartridge cases, decorative items. Zinc die casting, a method for manufacturing complex parts for automotives and electronics. Molten zinc is injected under pressure into steel molds. The result is complex-shaped parts accurate to tenths of thousandths of an inch. Zinc batteries, still used by the billions. Zinc powder in chemical industry. Zinc oxide in rubber industry, cosmetics, medicine. Zinc ointment heals wounds. World zinc mining, 14 million tons per year. China produces 40%, 5.5 million tons. Peru, Australia, USA, India, other major producers. Zinc price, around $3,000 per ton. The history of zinc as a separate metal began late. Europeans knew brass since ancient Rome, but couldn't obtain pure zinc. The problem, zinc evaporates when heated. Indian and Chinese metallurgists in the 16th century learned to condense zinc vapors in closed retorts. In Europe, pure zinc was obtained by German chemist Andreas Markgraf in 1746. But mass production began in the 19th century. Revolution happened in 1836 when French engineer Stanislas Sorel discovered the hot galvanizing process. He found that immersing steel in molten zinc protects from corrosion. This changed construction forever. Before galvanizing, steel structures rusted within years. With galvanizing, they serve for decades. The Eiffel Tower is painted, but many bridges from that era are galvanized and still standing. Today, without galvanized steel, skyscrapers, bridges, power lines, ships are impossible. Zinc, the invisible guardian of infrastructure.
And so, having traveled from explosions a mile deep through giant crushers and flotation tanks, through fluid bed furnaces at 1,650 degrees and retort towers at 2,200, through transformation into metallic vapor and condensation, zinc emerges, the bodyguard metal of modern civilization. The silvery metal that sacrifices itself, protecting steel from rust. The fourth largest metal by production on the planet, without which all infrastructure would collapse. Every time you see a steel bridge beam, a roofing sheet, or a car body, know they're protected by a thin layer of zinc as thick as a human hair. A layer that takes on corrosion, oxidizes instead of steel, slowly destroys itself, saving the structure. This is a story of nobility at the atomic level, how one metal protects another, sacrificing itself.
From underground explosions to silvery skyscraper beams, zinc's journey spans several weeks and 2,200 degrees. The metal that vaporizes to protect, that oxidizes so others don't rust. The invisible shield of 14 million tons annually, standing between steel and corrosion. Zinc. This is why bridges don't collapse, roofs don't leak, and cars don't turn to dust in 5 years. The guardian metal, the sacrificial metal, the metal without which the modern world would simply fall apart from rust.
Every year, humanity extracts over 2 billion tons of iron ore from Earth's crust. Picture this: more than half of our planet's entire weight is iron, most locked in the core, creating the magnetic field protecting all life. But here's what shocks engineers worldwide. We're standing on the most abundant metal in the universe, yet accessing it requires temperatures hotter than volcanic lava. How does rust-colored rock transform into gleaming steel skyscrapers? How do ancient mountains become modern civilization? Stick around till the end. You'll discover why iron shaped human history more than gold ever did, and the jaw-dropping secret hiding inside every bridge, car, and building around you right now. The story begins in Western Australia's Pilbara region, where iron mountains stretch across landscapes older than dinosaurs. Massive excavators, standing 8 stories tall, picture buildings that walk, tear into rust-red cliffs with bucket teeth weighing 12 tons each. These mechanical giants rip through rock layers formed 3 billion years ago when Earth's oceans first rusted. With thunderous crashes echoing across 40-mile-wide craters, each excavator loads haul trucks carrying 400 tons per trip. That's the weight of 80 elephants moving at 40 miles per hour on tires taller than basketball hoops. Processing 30 million tons annually from single mines, enough iron ore to build 12 Golden Gate bridges every single day. Next comes crushing, where house-sized jaw crushers, imagine dinosaur mouths made of hardened steel, pulverize boulders into gravel-sized chunks. With deafening roars splitting eardrums even through protection, these crushers generate forces exceeding 20,000 pounds per square inch. Clouds of red dust billowing upward create artificial sunsets visible from space satellites. Conveyor belts stretching 12 miles long, longer than Manhattan, transport crushed ore at 18 miles per hour. Workers riding inspection carts traverse distances requiring 25 minutes one way. That's enough belt to wrap around 300 football fields. Every hour, 50,000 tons flow through this system, weight equivalent to 5 Eiffel Towers moving continuously past checkpoints. Giant grinding mills, standing 5 stories tall, with diameters matching Olympic swimming pool widths, pulverize rock into fine powder. Inside these rotating drums, 20-ton steel balls, each weighing more than shipping containers, tumble with ore, creating grinding thunder heard miles away. Operators monitor vibrations. Wrong frequencies mean catastrophic bearing failures, costing millions. At rotation speeds creating gravitational forces triple normal Earth gravity, particles shrink to powder finer than talcum. Processing 8,000 tons hourly, that's filling semi-truck after semi-truck every 30 seconds. This powder, called concentrate, contains 65% iron. Magnetic separators then extract iron particles using forces strong enough to levitate railroad spikes, leaving waste rock behind. Next comes the blast furnace, a towering inferno standing 30 stories high, its steel shell glowing dull orange even from outside. At internal temperatures exceeding 3,000 degrees Fahrenheit, hot enough to vaporize aluminum instantly, iron ore transforms into liquid metal. Picture Dante's Inferno engineered with precision. Measured charges of iron ore, coke, and limestone descend from the top, while superheated air blasts upward at 2,000 degrees from ring-shaped nozzles called two airs. This creates a raging chemical storm, where carbon monoxide rips oxygen from iron oxide molecules. The reaction releases enough heat to melt granite. Every 3 minutes, sensors check 20 different parameters. Without precision, furnaces explode with force demolishing city blocks. The blast furnace operates continuously for 15 years, never cooling, never stopping, like Earth's core relocated to industrial facilities. Inside this chemical reactor, materials descend through distinct zones. Upper regions preheat incoming ore. Middle zones drive off moisture and carbon dioxide. Lower depths become hell itself, where iron liquefies. At the hearth bottom, molten iron collects at 2,800 degrees Fahrenheit, dense as lead but flowing like water. Every 4 hours, workers drill through clay-plugged tap holes. Liquid iron erupts in blinding white rivers, flowing through ceramic channels into railroad cars holding 300 tons each. This step is critical because timing determines metal purity. Tap too early, slag contaminates. Too late, furnace pressure ruptures containment walls. After tapping, slag, lighter impurities floating atop molten iron, gets diverted into separate channels. This glowing amber liquid, essentially liquefied rock, contains calcium, silicon, and aluminum oxides stripped from ore. Rather than waste, it becomes roadbed material and cement ingredient recycled at 98% rates globally. The molten iron, called pig iron, contains 4% carbon, too brittle for construction. Picture glass that looks metallic. Drop pig iron from waist height, it shatters into fragments. Next comes the basic oxygen furnace, where pure oxygen blasted at supersonic speeds through 3-foot diameter lances burns away excess carbon in 17 minutes. Flames shooting 70 feet high, temperatures hitting 3,200 degrees, create hurricane-force winds inside steel vessels holding 350 tons of liquid metal. Steel making requires precision rivaling brain surgery. Computer-controlled oxygen flow adjusts by milliseconds. Operators add exact amounts of manganese, silicon, chromium, elements changing steel properties dramatically. Too much carbon, steel cracks in winter cold. Too little, metal bends under load. Picture this: alloying elements get injected via submerged lances. Electromagnetic stirring, invisible but powerful, homogenizes composition. Samples extracted every 3 minutes get analyzed via spectrometers, determining chemistry within seconds. Modern furnaces achieve carbon content accuracy to 0.01%, difference between skyscraper standing or collapsing. After refining, liquid steel flows into continuous casting machines producing slabs 30 feet long, weighing 25 tons at rates of 1 slab every 90 seconds. This wasn't always so advanced. Back in ancient Anatolia around 1300 BC, Hittite metallurgists discovered heating iron ore with charcoal produced workable metal. That breakthrough, accidental furnace conditions reaching iron's melting point, changed human civilization forever. Iron tools outperformed bronze, enabling agriculture revolution. The breakthrough came when British inventor Henry Bessemer patented his converter in 1856, slashing steel production time from 24 hours to 17 minutes. Suddenly, steel costs dropped 90%. This single invention built modern cities. Skyscrapers, bridges, railroads exploded across continents. Today, global steel production exceeds 1.9 billion tons annually. That's enough to build 75,000 Eiffel Towers yearly, or manufacture 43 million automobiles, or construct bridges connecting every coastline on Earth. Carbon emissions drop by 62% when using recycled steel versus virgin ore, equivalent to removing 12 million cars annually. Industry saves over $80 billion yearly through scrap recycling. Processing costs drop 43% because melting scrap requires 1/3 the energy of blast furnaces. So here's the secret promised. Every ton of steel you see, bridges, buildings, cars, will be recycled indefinitely. Unlike plastic decomposing into microparticles or paper pulping into mush, steel never degrades. Magnetic separation extracts it perfectly from demolished structures. That girder in your office building might contain steel from 1930s locomotives. Your car's frame could include battleship armor from World War II. Nothing disappears. Metal merely transforms, reborn eternally. From ancient mountains to modern marvels, cycle completes. Iron, humanity's most essential metal, circulates through civilization like blood through veins. We're not consuming Earth's iron, we're borrowing it, briefly, before passing it forward to futures we'll never see.
Imagine a magnet so powerful it can lift a weight 1,000 times its own. How can a piece of metal stop a jet engine turbine or become the heart of a Tesla electric motor? The secret lies in rare earth elements, materials that hide more mysteries than gold or platinum. To create a single neodymium magnet, you have to move mountains of ore, melt metal at over 2,700 degrees, and use technologies that resemble alchemy. But there's a detail that almost no one knows about. Watch till the end, and you'll learn a secret that will change your understanding of the power of metal. The mining and initial processing of rare earth ores are a key stage in the production of neodymium magnets, as this is where the foundations for obtaining the necessary components are laid. This process begins with the large-scale mining of ore, containing the rare earth elements that make up neodymium. In the first stage, the ore is extracted from the earth using various mining methods. This can be either open-pit mining or underground mining, depending on the depth and type of the deposit. After extraction, large chunks of ore are delivered to crushing plants. At the crushing plants, the ore undergoes primary crushing. Large boulders of ore pass through a series of crushers that gradually reduce their size into smaller fractions. This is necessary for further effective processing and extraction of valuable components. The crushed ore may then be fed into mills for further fine grinding into a powder or a pulp, which consists of fine ore particles suspended in water. The next critically important stage is ore enrichment, the purpose of which is to separate the rare earth minerals from the waste rock. This process can involve various methods. One of the most common methods involves mixing the crushed ore with water and special reagents. These reagents selectively attach to the surface of the rare earth minerals, making them water repellent. Air is bubbled through the mixture, creating bubbles to which the hydrophobic minerals adhere and rise to the surface, forming a froth that is then collected. Heavier particles settle faster, allowing them to be separated from the lighter ones. Some rare earth minerals have magnetic properties, which allows them to be separated from non-magnetic components using magnetic separators. After enrichment, a concentrate is obtained, which contains a much higher concentration of rare earth elements. However, this concentrate is still not a pure metal. It requires further chemical processing, which usually includes dissolving the valuable components with acids or alkalis, precipitation, solvent extraction, and ion exchange chromatography. These processes allow for the separation of each rare earth element individually and its purification to a high degree. For example, neodymium is separated from other rare earth elements like praseodymium or samarium. The final result of this complex chain of processes is the production of high-purity neodymium oxide, which is then reduced to metallic neodymium. This metallic neodymium, in the form of granules or ingots, is ready for the next stage, alloying with other components to create powerful neodymium magnets. The entire process requires strict quality control and significant energy expenditure, but is absolutely necessary to obtain the raw material for the production of these strategically important materials. After the careful extraction and purification of rare earth elements, particularly neodymium, comes one of the most crucial stages in the production of high-performance neodymium magnets: alloying. This process demands extreme precision and control, as the final microstructure and, consequently, the magnetic properties of the finished material depend on it. The purified metals, neodymium, iron, and boron, are carefully weighed in strict proportions. These three elements are the main components of the alloy, providing its unique magnetic characteristics. In addition to them, small amounts of other elements such as dysprosium, terbium, cobalt, or copper may be added to the alloy. These additives are introduced to achieve specific properties, for instance, to increase the magnet's temperature stability, improve its resistance to demagnetization, or modify the material's brittleness. The exact composition of the alloy is a trade secret for many manufacturers and varies depending on the desired final characteristics of the magnet. The weighed components are placed in a specialized vacuum induction furnace. The use of a vacuum is critically important as it prevents the oxidation of the rare earth metals and other components at high temperatures. Oxidation would lead to the formation of undesirable phases, which would degrade the magnetic properties of the material. Induction heating ensures rapid and uniform melting of all components, creating a homogeneous melt. The melting temperature in such a furnace can reach over 2,700 degrees Fahrenheit. After achieving a complete melt and homogenization of the alloy, the stage of rapid cooling, known as the strip casting method, begins. This is a key moment for forming the optimal microstructure. The molten metal is poured in a thin stream onto a rapidly rotating, cooled drum. Contact with the cold surface of the drum leads to an extremely rapid cooling of the melt at a rate of up to millions of degrees per second. This extremely rapid cooling prevents the formation of large crystal grains and allows for the formation of an amorphous or microcrystalline structure. Instead of the typical crystalline structures formed during slow cooling, extremely fine grains are formed. This process is also known as rapid solidification, and it is fundamental to achieving high magnetic properties. The resulting material takes the form of thin, easily crumbled flakes or ribbons. This unique microstructure, with very fine, often anisotropic grains, is the key to the high strength of neodymium magnets. The smaller the grain size, the more difficult it is for the magnetic domains to change their orientation, which provides high resistance to external demagnetizing fields. Thus, the alloying and rapid cooling stage is fundamental for forming the magnetic characteristics that will later be locked in during subsequent production stages. After the alloying and rapid cooling stage, when thin flakes or ribbons of the neodymium iron-boron alloy have been formed, a stage called hydrogen decrepitation begins. Every year, millions of tons of chemicals are produced worldwide, but one of them, chlorine, is truly staggering in scale. In the United States, over 12 million tons of this gas are made annually. That's the same weight as 120 Gerald R. Ford aircraft carriers, the heaviest ships in the world. But where does this dangerous, yet vital substance come from? It all starts not in a lab, but in underground deposits of common salt. From there, it involves electricity, membranes, and an entire industry that consumes more power than entire American states. And if you watch till the end, you'll discover the secret that chlorine hides behind its sharp smell. The United States is one of the world's largest producers of chlorine. Each year, plants in the country produce over 12 million tons of the gas. This number is just hard to wrap your head around. Imagine the weight of the aircraft carrier, the Gerald R. Ford, the heaviest warship in the world. It's about 100,000 tons. This means that in a year, American industry produces as much chlorine as 120 of those aircraft carriers weigh. This enormous quantity makes chlorine one of the top 10 most produced chemicals in the country. It all begins not in a laboratory, but deep underground. The main ingredient for our recipe is common rock salt, or sodium chloride. But it doesn't arrive at the plant in salt shakers. It's either mined in the form of huge chunks, or, far more efficiently, pumped out from under the ground. Water is pumped into deep underground salt deposits. The water dissolves the salt, creating a saturated salt solution called brine. And it's this concentrated, salty as tears solution that is our raw material. But it's still impure. It's full of contaminants, calcium, magnesium, and other minerals that can clog up our expensive equipment. So before the main show begins, the brine goes through a thorough purification process. It's passed through a whole series of tanks where chemicals are used to precipitate and filter out all the impurities. What comes out is a perfectly clean, clear, and very salty solution, ready for the main event, electrolysis. Now, let's head to the heart of the plant, the so-called cell room. This is a huge loud hall filled with rows of strange enclosed tanks connected by a network of pipes and thick electrical cables. These are the electrolyzers, or cells. This is where all the magic, or more accurately, all the chemistry will happen. Let's imagine one such electrolyzer. Essentially, it's a box into which our pure salt solution is poured. And into this solution, two electrodes are submerged, a positively charged anode and a negatively charged cathode. Now, a direct electric current of colossal power is applied to these electrodes. And this is where the split begins. The salt molecule in the water breaks down into positively charged sodium ions and negatively charged chloride ions. The electric field forces them to move. The positive sodium ions are drawn, as if by a magnet, to the negative cathode, and the negative chloride ions to the positive anode. And it's at the anode that the whole point of the process occurs. Each chloride ion that sticks to the anode gives up its extra electron. Two such chlorine atoms, having lost their charge, immediately pair up, forming a molecule of chlorine gas. Billions of these molecules gather, and tiny bubbles of a greenish-yellow gas begin to appear on the surface of the anode. This is our chlorine. The main resource for chlorine production is electricity. The chlor-alkali industry is one of the largest consumers of electricity in the entire US manufacturing sector. To produce 1 ton of chlorine, it takes about 2,500 kilowatt hours of electricity. Now, multiply that by 12 million tons a year. It turns out that this industry consumes about 30 billion kilowatt hours annually. That's more than the annual electricity consumption of entire states, like Vermont or Wyoming. It's like an entire city of 1 million people, working year-round just to split salt molecules. But what's happening at the cathode? The sodium ions have drifted over there. But they don't turn into metallic sodium. Instead, the electric current splits the water molecules in the solution into hydrogen and hydroxide ions. Bubbles of pure hydrogen are released at the cathode. That's our first byproduct. And the hydroxide ions left in the solution combine with our sodium ions to form sodium hydroxide, or caustic soda. This is our second, incredibly valuable byproduct. But here, a huge problem arises. We've just created 3 substances: chlorine, hydrogen, and caustic soda, and they must never be allowed to mix. Chlorine and hydrogen together form an explosive mixture, and chlorine and caustic soda react to form bleach, which is not what we want at all. So, the genius of the technology lies in separating these 3 products at the very moment of their birth. This is done using special membranes or diaphragms. Imagine a thin, paper-like, but very clever partition standing between the anode and the cathode. This membrane, made of a special polymer, is like a bouncer at a nightclub. It allows the positive sodium ions to pass through to the cathode, but blocks the negative chloride ions, preventing them from getting into the cathode space. This way, chlorine is born and collected in one part of the cell, while hydrogen and caustic soda are in another. Now we need to collect our harvest. The moist, hot, greenish-yellow gas is continuously pumped out of the anode chamber. First, it needs to be cooled. It's passed through heat exchangers where it gives off its heat. Then, it needs to be dried. Chlorine is incredibly aggressive, especially when wet. It corrodes almost everything. But there's one substance it doesn't touch: concentrated sulfuric acid. So, the wet chlorine is passed through towers where it bubbles through sulfuric acid, which, like a sponge, absorbs all the water from it. The resulting dry, cool, but still gaseous chlorine is ready for the next stage: liquefaction. It's compressed under enormous pressure and cooled at the same time. Under this double whammy, the gas turns into a clear, amber-yellow liquid that looks like oil. This liquid chlorine is much easier to transport and store. It's poured into special thick-walled steel tankers, or rail cars. Every step of this process is carried out under completely sealed conditions, because a leak of this gas is deadly. And what about our byproducts? They are no less important. The hydrogen we've produced is collected, purified, and used either as fuel for the plant itself, or sold for ammonia production, or in the food industry. And the resulting caustic soda solution is pumped out, concentrated by evaporating the excess water, and sold. It's one of the most important products in the chemical industry, used to make soap, paper, aluminium, and much more. And so, from simple salt water, by passing a huge amount of electricity through it, we learned to obtain 3 extremely important substances at once, which form the foundation for thousands of other products that surround us in our daily lives. Now let's see where all this enormous amount of chlorine goes. You might think it all goes into disinfecting swimming pools, but that's just a drop in the ocean. In fact, less than 5% of all chlorine is used for water disinfection. So where does the other 95% go? It's a key building block for other products. About 40% of all chlorine goes into the production of this universal plastic. The vinyl windows in your house, water pipes, medical IV drips, vinyl records, the credit card in your wallet, all of these were born thanks to chlorine. Another 40% or so is used to create thousands of other organic and inorganic compounds. Pharmaceuticals, solvents, refrigerants, herbicides, insecticides. The list is endless. Chlorine is also a key component for bleaching paper, giving it that clean white color. And finally, about the byproducts, which are actually no less important. We remember that for every ton of chlorine, we get about 1,100 tons of caustic soda. This means that American industry produces over 13 million tons of this vital alkali annually. This makes chlor-alkali production a perfectly balanced business. When the demand for one product falls, the demand for the other can rise, allowing plants to operate stably. So these millions of tons are not just statistics. They are proof that this sharp, suffocating gas is the invisible foundation for a huge part of the American economy. From the plastic pipes under our streets to the medicines in our pharmacies.